Okay, excellent. Okay, excellent. So we are going to talk about today on MLOps and especially focus on the MLOps side for training jobs. We will be showcasing MLRun. It's our open source MLOps orchestration framework. We will talk generally about what why is MLOps starting to get into the buzzword game. Everyone is starting to use MLOps this and MLOps that. So we will talk about why is it important. We will talk how MLRun is guiding you and help you glue everything together and make it essentially very easy until like almost one command away from deploying your model. Then we will focus on only one of the key features of MLRun, which is related to model development. And then we will have a live demo, how we train the known and loved MNIST classifier and take it from development into production. MLOps. MLOps is basically the set of tools that are needed to take your research and make it live for the users to use it. But did anyone try to deploy his notebook somewhere in a cluster in a server? It's not that easy. Once it's working in your notebook, it's not that simple to now put it in a Kubernetes pod and make it scalable and write it an API for the model for users to access it and so on. So what is basically happens is that almost 85% of models do not see the light of day regarding production. What is usually the case is that data science teams are focusing on research and developing and training the model on small scale, on maybe in their private laptops even. And once they are done, they simply throw the model over the wall, quote unquote, into the other teams, which are now need to take the models and make them work with real-time data pipelines, make monitoring and so on. So what usually is being done is that you have your pool of data, you have images, text, whatever. You make some data preparation, maybe a little bit of feature engineering. Then you write your training code, you evaluate, you're happy with the result. And now, what now? Now it's getting into the real world. If you want to take your model into production, it looks something like this. Now you have all your data preparation and feature engineering that comes into real-time data with Kafka streams and maybe Spark engine and so on. Then you have to monitor your model with a time series DB to get all the traffic and to store all the predictions. You need to retrain and optimize your model for performance. You need to write an API to serve it, and so on. It's become a really, really big mess that requires a lot of engineering teams to deploy. So as you just seen, the development is just the first step. You have to package everything, you need to scale out, you need to tune it, and so on, which usually can take even months of work. So MLRun is here for you. And in MLRun, we developed it with a production first mindset. What this means is that why develop your models in training environment that is not production proof? We want to take the data scientists to working in their own IDE and their own frameworks but make it so that with one click, they are always one click away from deploying their model. So accelerating the data science is becoming a real necessity. And as you can see, instead of simply developing it one step at a time, MLRun is enabling you to simply wrap it all around in one package with an automated, fast, and continuous development approach. So how MLRun is doing it? Well, serverless is the magic, just like the caption is saying. Everything in MLRun is simply a function. There are a lot of types of function, but basically each function is dependent and can be on its own. And it looks something like this. So you have your code, which is this gray box, and then you create an MLRun functions. We will see it later on in the demo. Now this function can be type KA's job, it can be a local, it can be a Nucleo, it can be OpenMPI, and so on. And once you have this function, you can now run it remotely, locally, wherever you like. The function still gets its input, it gets data, secret parameters, and once it runs, it's track everything and every single log and output it yielded. So it provides seamless tracking of all your work and all of your running functions. So MLRun's key component are the following. We have the feature store, we have the real-time serving pipeline, and we have the model monitoring, and we have the fully automated CI/CD for models and machine learning in general. Today, we will focus mainly on the training side, and we will even see some of the real-time serving pipeline. We will build a pipeline for the MNIST model, but let's go it really quickly on the feature store and all of these key components. So the feature store, as you can see, is at the core of enabling the taking the models to production very fast, because everything is related in the feature store. If you have your data in real time, you can have a real-time pipeline that will do all the feature engineering. Every single feature is then stored in the feature store and can be taken to train on an offline snapshot. The model monitoring is using the feature store to write its own monitoring metrics. The feature store is really core and very strong component in what makes MLRun what it is. Any question so far? Okay.
Can you elaborate a little bit more on the feature store?
Yes.
What is the insight? Can you go to that box, like connect, transform, serve, catalog? My understanding is a feature store basically is that storing all the feature, including the raw and all those has been transformed and versioning.
Yes, so the feature store is basically when you do your feature engineering, let's take the classic one-hot encoding. So you one-hot encode data, and now you have your new features like that labels O's and ones. So you don't need to do it every single time you get new data, because now you can have this step as a graph of the feature store. And once new features are arriving, which is basically new data, they will come through this pipeline, and you will get this one-hot encoding automatically to be ready to be inferred through your model, and even registered in the monitoring service. Did it answer your question?
Yes, thank you.
Sure. Feel free to interrupt and stop me whenever you have question. We are here to learn and have fun, so if you have question, shoot it up. So the feature store is the word is okay, never mind. The feature store can work on any type of data, whether it's structured, textual, visual. It's just a matter of writing your own steps into it. The feature store can work also on multiple engines like MongoDB, Spark, Pandas, and so on. And here you can see even we have a screenshot of a pipeline. Sadly, I can't see the steps, but you can see like this is some sort of pipeline that the features go through, and you can get all these features. By the way, I see you writing in chat, but I don't see the chat. So let's see. Okay, I will try to answer everything later on. Yeah, I hope it's fine by everyone. Okay, so CI/CD, MLRun is modular and can be integrated to any CI/CD tool, whether it's GitHub Actions or Jenkins and so on. And it can make it can automate the retraining process and even optimizations and so on. Everything can be triggered. You can have your notifications for Slack via mail, whatever you like. And okay, that is just the CPU and GPU assignments. We will see it later on. Here you can have the MLRun is using Grafana to showcase all the metrics and usage of the GPUs and CPUs and memory and so on. And now the real-time serving pipeline. Okay, so the real-time serving pipeline is using Nucleo. Nucleo is also an open source serverless framework that is also developed by Iguazio. It basically takes your Python code and make the model into a model server, which is exposing the model to an API, which you can later on use for your applications. For example, as we can see here, we have the some sort of enrichment for the data. We have a pre-processing, and then we have an ensemble router that have 3 models. The ensemble routers can have like a major selection, and then it goes to a post-process, and then it responds. It is very easy. You can see, okay. It is very easy to see to set this graph. It's use a very straightforward API, which we will see it later on in the demo. Here is another example for a distributed real-time serving graph. We have a serving graph here that goes into another serving function. Every function is using Nucleo. So there is a Kafka stream that goes into a data preparation serving graph that then goes to probably the model with the GPU and then into the post-process. So the last key feature until we arrive at I'm sorry, I'm trying to move the Zoom camera. Oh, finally, I got it. Okay, so here you can see the model monitoring. Model monitoring is a very important tool because you basically want to know how your model is performing. So you need to track like the confidence of your model, like if it predicts the class 2, but with a confidence of 32%, then the model is not performing very good, or maybe it's not his fault because the data drifted. So we have a data drift and concept drift, and it's very important for the experience and the usage of the application, so the models can stay in shape. So the model monitoring is a very interesting tool by itself. I can't, like the feature store, I can't over-explain it now because we won't have time for the demo. This is one of our customers, an example for one of our customers. It has a factory which take images. The images then go to a Kafka stream and an object key value. It uses the training on GPUs using Horovod, the distributed training, which we will see in the demo today. Then it goes into an Onyx optimization, validation, and deployment. Now the deployment itself is, again, it's a Nucleo, but it's a serving graph. So even this is built upon all of these steps. We will see serving graphs, we will see Horovod today. Okay, so model development with MLRun. So I want to showcase like our credo list of what is in our eyes considered to be a healthy training environment that uses MLOps quantities. So first and foremost, it should have experiment tracking. Okay, experiment tracking is the possibility to learn from the past and compare different results yielded from different parameters in an easy, convenient, and insightful manner. Everything, like I said, in MLRun is a function. Each function you run is logged. What is logged is usually artifacts. Artifact can be models, can be dataset, can be plots, files, and so on. So by using MLRun in itself, without anything extra, you gain full experiment tracking of whatever you do. It's very important that, you know, models are basically learn from the past. They get data sets, they learn from the data, and then they know how to predict on the assumptions that the data will return itself. So we as the data scientists, we should also learn from the past and seeing the experiment history and what we did and what parameters we used is very important for achieving the best results. Integrability.
One question,
yes.
question, please. So, as data scientists, we start from getting the data to building the model and evaluating it, right? The ML ops, how does it come into picture? Because ML engineers are there. What is the interface there in between? What is the role interface between data scientist and ML engineer? Why should a data scientist learn about ML ops?
Okay, so when a data scientist is finished with his research, for example, you focused on some, I don't know, like some sort of bone images, and you build a convolutional network that's spot on, get 90% accuracy, and you're very happy with it, and everything is good. Now taking it into production is a lot of work, as we saw in the previous slides. If a data scientist can have the production mindset and research with the production mindset, then it will reduce the deployment time of his model, because in real time or in real life even, the images are not located in some sort of a CSV file, and the CSV file is not conveniently located in your directory, and you can't load everything like in your Jupyter notebook. So doing everything in a system that can automatically deploy everything is, in my eyes, is very beneficial.
Oh, okay. Got it. So you're saying that if a data scientist has an understanding of how deployment is done, that mindset will be where he'll start to work on it, model building, right?
Yes.
So
Also,
the glitches are less later on.
yeah. Also, what we will explore today are very quality of life features for the data scientists. We will see later on, we have a function marketplace, we have this experiment tracking, we have auto logging, we have distributed training, we have a lot of tools that will focus the data scientist on data science rather than on writing code and maybe fight with Plotly to make his graph smoother or something like
Got
that.
it. Got it. Thank you.
Sure. Okay, so integrability is also a very important aspect in a healthy training environment because each data scientist or a data engineer is used to work on some sort of a vendor or an IDE or an ML framework, and a training environment should not limit his choices. So in MLRun, we currently support all of the above on the screen. Of course, there are also custom and manual techniques that you can apply to insert unsupported frameworks you don't see here, but we are always putting more integrations into the system. From the ML framework side, I can tell you that PyTorch Lightning is coming and Cat Boost. So these two, for example. Resource management. So to be cost efficient is very important in our days, and GPUs becoming a very rare tool. So with MLRun, once you have your function and you can configure it to use the resources it requires. You can choose the number of workers, you then assign CPUs, GPUs per worker, and then you distribute using either Dask or Horovod. The distributing, if using the frameworks you saw in the previous slides, is being done automatically without code changes, without anything. Which brings us to the next feature, is this ease of use. A training environment is nothing if it takes years to adapt and to learn. In MLRun, the ease of use is from the beginning. It's a simple one function that you insert your code, and it wraps around with MLRun, and then MLRun can control it, and it can be turned into MLRun function with auto logging, distributed training, file management, and so on. And even if you don't want to write your own code, we have a lot of functions that keep on coming to the MLRun function marketplace. Sorry, can you put on mute? Okay, thank you. The function marketplace is where you can simply import functions that we in Iguazio wrote or other users wrote, and you can use it in your project to run on your own. And the last but by no means least, it should be production proof. And I will read it because I have the sentence, is the ease of mind where once the development of the model is done, the production is just a small step ahead. So we will see that it is really a small step ahead in the upcoming demo, which is now. So let me stop share for a moment.
But just a question here, Guy.
Sure.
So that means that you definitely have to have your own infrastructure in place where you can run the MLRun service or somehow, which is the deployment service, right?
We have in the MLRun docs, we have a very simple set of commands that will install MLRun in your system. I can guide you through after the lesson and show you. It's very simple. You know what? I will get into the, just looking for the
Sure,
oh,
sure. But if you're talking about enterprise scale, so is there a favor for anything, something like OpenShift or Kubernetes, or should you rather go with a managed service on AWS? What is your experience there?
It's a very good question. So we in Iguazio have an enterprise solution with basically, you will see it in the demo. I am using the Iguazio cluster that runs MLRun. You can try and play with MLRun locally, and it is open source, so you can of course use it. But we have also AWS. You can deploy Iguazio service in AWS. And yeah, so that's it. Dr. M, I don't want to butcher your name, sorry. Zuhair?
Yes, sorry, Guy. How do you compare this product to open source products like Flask, Django, Streamlit, and maybe with Heroku, Azure service? So how do you compare between your product and these open source products?
So the only open source I used before developing MLRun was MLflow. MLflow is very cool package, and you know, you can. The best answer I can give is you should try everything, and you will choose your favorite. I can't know like every framework in the world currently, but I hope you will like what you see now.
Okay. So thank you.
So for your question, this is our doc site. You can see here the tutorial installation. Okay. So no, this is not what I wanted. Okay, so that's what I wanted to say. You simply use pip install MLRun, then you configure your remote environment, and you can even simply download a Docker image. Which I don't see for some reason. Wait a second. Never mind, I will get back to it. I want us to have time. Okay, so we will now have the live demo. It is live, so I hope there won't be any live errors, but we'll see. So we have 4 notebooks ahead of us.
Can we get the link to this Jupyter Lab?
I will send it. I will send it like later on. Okay.
Okay. Thank you.
It will be in the docs very soon. It's kind of new, so it's you know, it's in a pull request currently. So
yeah. Okay.
Okay, so we have the first notebook is the model development itself. Then we have an example for hyperparameter tuning. We have another notebook for distributed training. And then we have model serving, which will build a serving graph using Nucleo, as we've seen in the presentation. So we will begin with a little code review. It's MNIST. I think 99.9% of you knows what it is. It's a handwritten digits, very, very common data set. We will be using TensorFlow Keras. And what is new here is that we will use MLRun frameworks TF Keras. Frameworks is the sub-package inside MLRun that has like a lot of cool features that can wrap your code with MLRun like with one line solution. So we will see later on when it is used. So we will get the data set using Keras data set, MNIST low data. Nothing is too unique here. The labels are going to be categorical. We will create our model. For this demo, we will be like a little bit of an overkill for MNIST, but it's just for the demo's purpose. We have a convolutional block, which is made of 2D convolution, ReLU, batch normalization, max pooling, and then dropout. And we have a dense block, a dense ReLU dropout. So the get model method is receiving conv block and dense blocks. So it will be, we can experiment on what combination yields the best model in the short Epoch training time we will see. So here is how I built it, nothing too special. And now we'll go to the training code. The training code, again, is very straightforward. We have the get data set. We simply get a model. And then we have this line, apply MLRun. Apply MLRun is, just by its name, is applying MLRun to this code. This is only the line that is very unique in this code. Otherwise, the training code is straightforward. Get dataset, get model, we compile, and then we call fit. The only thing I added is this line here. Now what it gets the model that I want to wrap around with MLRun, and it gets a model name that I want to give the model inside the MLRun database. And we have the evaluation code, which is even more simple. To evaluate, what you need is a model and data. So the data is being returned from our method get dataset. And the model we will send a URI, which we will later see. And apply MLRun will get the URI and it will load it automatically into a model handler. Model handler is a class by MLRun that has 4 jobs. It loads a model, it saves a model, it logs a model, and it updates a model artifact. So here, apply MLRun is loading the model automatically from the model path. And when we want to access the model, we simply call .model, and then we call evaluate. So let's run it. We will create a project. So project, like we see, project is the main component of MLRun. Project have underneath it all the artifacts and all the functions. So project can be later on maybe imported and exported into Git. You can send projects to your colleagues and so on. Sorry. So how we create it, we simply call MLRun.get or create project. We give the project name, MNIST classifier, and user project will simply concatenate my username into the end of the project. So it is created, and now we will use code to function. Now remember the MLRun function. So I want to turn my code in this Jupyter notebook into an MLRun functions that I can run remotely on a Kubernetes or on an OpenMPI. So what I need to do is just mlrun.code to function. I give my function a name. I give it kind. Kind is what type of function I will create, whether it's Dask, whether it's OpenMPI, whether it's a simple KH job, which is what I did here. And I'm giving it an image. So my image is ML models. It's a cool image with a lot of frameworks like PyTorch, TensorFlow, and so on that I use. Now I want to take this function and set it into the project so I can load it later on in the next notebooks. So all I do is simply set function, give it a function object, and then I call save. Now how the project is saved, it's simply saved in, yes, sorry? Okay, never mind. How the project is saved in this YAML file. You can see here the source code. You can see the image. This is the function that we just set, and that's the name of the project.
So one question here. I think what
yes,
what is like really important is to rebuild the same environment a data scientist has been using during experimentation phase to be when you are in production, right? So now I know you just imported TensorFlow, but there might be differences between TensorFlow 1.3 and 1.3.2 or 1.3.5. So how do we ensure that you are using the same exact versions in experimentation and production phase?
Okay, so I will use the same image for running my serving function as well as my training function. So if my training function is using and my serving function are using the same image, I know for fact that they will have the same environment. Now, if you want to write your own image or maybe even build it with MLRun, MLRun can have additional commands that will run on top of the image before it will run its code. So you can edit the image before each run. It's very important, and it's a very good practice to make sure your environment is the same in both the training environment and the deployment environment, especially for pickle files. So that's a very good question, and this is how we...
That's the reason I was asking, yes.
Yeah, so if you set the image and you work neatly, you won't have any problem with it.
And you also have the option to update the images from within the Jupyter Notebook, question mark, or?
Yes, you can. You can you can access the spec of the function, and then you can simply write requirements. You add the list of requirements, and when you call, I can call, for example, I can do this dot deploy, and once I call deploy, the image will be built with the requirements you added to it.
Okay, so that was, I think my intention was to understand if you are building the environment where you are running the code in experimentation and production phase explicitly and not like implicitly somehow, but that clears it. Thanks.
Sure. Okay, so now we have the model, and we will run it on the local Jupyter notebook because I set local equals true. As you can see, it ran. I have a very high accuracy, and now I have this summary table. So what I can see here, Here I can have a link to the MLRun UI. This is the MLRun UI. You can see here my job. This is the project. My training function. I can't see. The zoom is very blocking my screen. I want to move it. Well, basically, I will click the evaluation. You know what? Wait a second. Maybe if I click here. Okay. Now I see. Okay, so we have the training function. I can see the result that was yielded. I can have labels. I can see all the results in this table. I can see the logs that were logged from the pod, and I can see all the artifacts. So keep in mind, I didn't plot anything. I didn't added anything. All I did was adding a single line called apply MLRun, and everything is tracked. You can see here the training accuracy. Once it's finished loading, okay, excellent. You can see everything here. The graphs are using Plotly, and we have the model object as well. The learning rate values are also being tracked, but because we don't have a scheduler, it's the same learning rate each epoch. We will run Horovod, and then we will see the learning rate changes because we have a scheduler in Horovod. Okay, let's go back to the Jupyter. Well, here I talk about automatic logging. So we have all the logs can be seen from the training run object. I didn't talk about it, but once I hit run, I get a training run object. So all of the results will be accessed via the run object. So you can see here, when I hit outputs, I have the model name, all the plots, and so on. I can even access the artifact in the Jupyter Lab. So if I want to see the training accuracy, I can see it right here. And viewing the MLRun UI, as we just saw. So in addition, we use Tensorboard as well. So if you're used to Tensorboard, you are in for a treat because you can see here all of the run. Wait, this is the runs I use for the hyperparameter tuning, which you will see this is why it's a little bit messy. But as you can see, everything is logged, including the graph that we just used. And in addition, it is fully integrated into MLRun via the text. You can click here to go straight to the UI and the function itself. And we even have the hyperparameter tuning table, which is not a lot of people know about this, but it's a very cool feature of Tensorboard. It's a bit tricky to set up, but once it is, you can see here what yielded the best result from our hyperparameter tuning task. We will see it later on. So I can click here. Now I can see all the plots that yielded these results and so on. Okay, any questions so far?
Yes, Guy? Yes, sorry.
Yes, sure.
Okay, so is there a graphical user interface for, I mean, rather than using the notebook, we can use a graphical user interface? This is question number one. Question number two is there isn't any GUI. This notebook is working locally, or it is overloaded on the server or your server like Google Colab. So everything we run will be run on your server.
So you need to set up MLRun You can follow in the docs how to set up locally in your computer or in Google Colab. We support Colab, PyCharm, basically every IDE. All you need to do is pip install MLRun in your local machine, and in the remote machine, you need to have the environment variables, which are later you simply set them as environment variables, like username, password, and so on. So MLRun can connect to the remote MLRun DB and log itself there.
So we cannot run the notebook on your server?
You can have, if I remember correctly, you can have like a free trial in the Iguazio website, where you can have like a full Iguazio cluster, which you can have a Jupyter and you can run whatever you like. We have multiple demos. Okay, this is kind of a new, it's more of a tutorial. There is a lot of text here, which I skip because I'm talking. But we have in MLRun demos, which is another repository, we have a feature store demo, we have a mask detection demo. We have a lot of good examples there.
Okay, thank you.
Sure. So here is the evaluation job. We simply call run. We choose the handler evaluate. And what is cool here that we take the training run object outputs model, which is basically returning a model artifact, and it's being sent into the function, and the model is being loaded and is being evaluated. Again, you can see the evaluation graphs and so on. For example, here I can go to the last batch and see why it's not behaved like the others. And that's it for autologging. It's important to remember that you can take your code, you can add apply MLRun, okay, because this code is very, very straightforward. All we did is use this line. Now let's talk to hyperparameter tuning. So this I ran in advance because it takes a very long time, as you saw in the Tensorboard, all these runs. So it's a new notebook. I want to run my function, but with hyperparameter variables. So I need to load my project. So I set a name and then I call the exact function I used to create a project. Now it will know there is a project called MNIST classifier guy L, and it will load it. So you see loaded project MNIST classifier. Now our function MNIST development should be now ready to use. So how we achieve the function? We call project dot func. Sorry, I talked in Hebrew for a second. Dot func and give the function name. So now I got the function, and then I can simply call run, and I will run my hyperparameter tuning task. Now, how does hyperparameter tuning work? So we have a strategy, we have a selector, and we have the hyperparameters dictionary. So a strategy is how to choose the hyperparameters values in each run. So we have the random, which in my experience perform the best for most scenarios. We have the grid and we have list. Custom is that you give the permutations and it will use the manual permutations. Selector is how to select the best model out of the hyperparameter tuning job. Now we will simply want the validation accuracy as the highest. So I will call max.validation accuracy and we'll take the maximum validation accuracy. And of course, we need the hyperparameters values, so we give it a dictionary. Now we will search which combination of blocks will yield the best results. Now, of course, it's a little bit nonsense, because if I give the same epochs in the same training time, so very big networks won't achieve very good results, because they need more time to train all the weight parameters. But for the demonstrations, I think it will do the work. So I will create a new task using the MLRun task. I will give the static parameters, so I will train for 3 epochs. And now I will give the hyperparameters. So I will take all these configurations and give the task the hyperparameters configurations. Now, once I load my function, I can simply call run, and it will start deploying a pod, Kubernetes KH job, and it will train there. So you can see here, I have epochs 3, conf blocks 1, dense block 0, and you can see Tensorboard is loading, yada, 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 and you can see here the 3 epochs. Now it's done, loading the next batch of parameters and another training. And this is how it is doing until we see this one. And I can review my results in MLRun. Everything is tracked, everything is saved, everything is logged as usual. But what is being returned to the training run object is only the best model. So, but in addition, I can see the parallel coordinates plot, which you can see here. So I can see, okay, live demo, guys. Don't know what happened. Well, let's access it from the Artifacts tab. So let's go to the Hyperparameter Tuning job. So this is my Hyperparameter Tuning job. You can see here the results. I can see that iteration number 3, which did with this parameter, 3 conf blocks and 0 dense blocks. This one won the battle. And we can see his artifact. So now we should be able to see the parallel coordinates. Wait a second. My bad. The Zoom screen is always interrupting me. Okay, now we can see the parallel coordinates plot. We want to choose the metric validation accuracy. So we can see that indeed iteration 3 yielded the highest validation accuracy. This is why he won. Any question on hyperparameter tuning? Okay. Let's wait for it to load. Okay, so let's go over to distributed training. So distributed training is a very important tool if you have very big models. Now, models today can be huge. They can weigh tons of gigabytes. The data set which they are training on is also enormous, and it might be very long to train on a single GPU or even a single machine. So the option to distribute your training is is almost a must-have in these scenarios. So we want to see how MLRun is distributing your training without essentially changing your code. So because we added apply MLRun, we will now use distributed training using Horovod. Horovod is developed by Uber. It's a distributed learning framework. Basically, in a very high level, it splits the data set between the amount of workers you choose, and then only the master worker will update the weights with the average of the gradients. So the back propagation of each gradient, and then all the gradients will be averaged, and then the weights will be updated. I'm sure it's more complicated, but that's like a very simple explanation of it. It is working over OpenMPI, and that's what you need to know in order to distribute the training. So again, we will load the project, and now we will create our function. This time we will choose the kind as MPI job. Okay. Now you see I'm taking the notebook, the model development. It's the same notebook. Nothing changed. The only thing that's changed is the kind. It's an MPI job. Before it was a regular K8 job. Now it's an MPI job. And because MLRun will detect it's an MPI job, it will automatically initialize Horovod and it will start working. So here I set the use GPU to false because I'm scaled to 0 on the GPUs. I don't want it to take time. I didn't think I ran it everything. So wait a second. Let's reset the kernel and start running. Okay, everything is loaded. Now I'm creating my function on the MPI job function. Now I don't want to use GPU. If I were to use GPUs, then you assign GPUs to the function simply by calling .gpus. Then you give the amount of GPUs per replica. I will set 2 replicas. And by the way, the image, if it interests you guys, then basically it's the same image, but this image has both Horovod and CUDA. So it will be able to use GPU. So I'm having 2 replicas, and now all I need to do is call run. Okay, what happened? Of course, wait a second. Maybe I gave it a wrong name. Okay. And now we will call run. Why did I change the name of the function before the workshop? I don't know. Okay. So the function is starting. As you can see here, I have worker 0, worker 1. Wait a second. Sorry, guys. Okay. Now you can see MLRun is telling me Horobot worker 0 is using CPU, worker 1 is also using CPU. And now they're both started the training job. Everything is also logged to both MLRun and Tensorboard. I can see it live here now. Wait a second. Let's turn off all of these guys. Okay. So this is our current run. As you can see, the learning rate is automatically being tracked. Now let's wait for the Epoch to finish. In the meantime, we can also pop over to the UI. And you can see this is my function. It's type Horobot. I will click on it. I can see the pods. So I have my launcher, which is basically the manager of both workers. I have workers 0 and worker 1. And I can see the artifacts. No artifacts currently. Let's see where they are. Again, I need to move the camera. Okay. Well, it takes time. I will wait one epoch and then we can move on. Any question regarding the Horobot distribution?
I do have a question.
Sure.
Can you hear me?
Yes.
It might be a stupid question, but I'm genuinely interested to know if the distributed training it trains the same model on maybe more than one CPU. So, for example, if we have two computers, for example, we can train on one CPU and on one CPU, and then the main, or the I don't remember the name of it, averages the weights of or for example the gradients of the two workers, and then updates the weights. Is that what distributed training is?
Yeah, so distributed training is simply split the workload between the resources you provide. So now Horobot will use 2 CPUs instead of 1, and it will use 2 workers. So how Horobot works is basically simply average the gradients, but it's not that simple. You can go over to the Horobot documentation site. They have a very detailed explanation there. They even have the original paper they used in order to develop the Horobot framework. But when using Horobot, just think of it as you train the same model, but it trained like, what's the word? Simultaneously on 2 lines. So you have, instead of simply just 1 line of forward propagation and backward propagation, now you have 2 workers doing forward propagation on half the data and then backward propagation on half the data. And the average of the gradients is what's updating the weights. Okay, so it turns out as faster.
Thank you.
Sure. Let's see. Well, I don't know why it is taking so long. Okay. Well, never mind. We can hop to the serving. So now we want to take the model we just trained and researched with the conv blocks and dense blocks and so on. And we want to serve it in a little Jupyter notebook magic. Okay, I will use the IPy Canvas, which is a cool widget that you can draw stuff on a Jupyter notebook. I wrote a little blank square that you can write with the mouse. So I can basically write digits, and then it will send over to a nuclear serving graph we will write now. And it will tell me, using my model, it will tell me what digit did I write in the block. So we will write a very simple serving graph. We get the image pre-processing phase. Then it will go into the model, and then it will go into post-processing, which will simply wrap around the prediction of the model in a dictionary, so it will be more readable later on when I print it. Okay, so the steps are as we saw in the first notebook. This is my serving code. I have my pre-process, so the pre-process simply turn the array that it gets to image. I then grayscale the image, resize it to 28 by 28, which is what my model expects. I do expand dims for the batch dimension, and then I will send it over to the model. And the post-process is what is getting from the model. So all I do is simply take the softmax output and take the softmax output and then return the predicted digit and the confidence the model produced. So okay, the TensorFlow Keras in the frameworks package have a pre-built TensorFlow Keras model server. It can be used straight out of the box with the model artifacts that were logged with the apply MLRun function. Of course, MLRun is very modular and very abstract. You can write your own model servers, you can write your own model artifacts and so on. But for this example, we will use the pre-built TensorFlow Keras model server. We will load our project, and now we will use code to function again on this notebook to have our serving code. Now the kind is not a job, not an MPI job, it's a serving, so it will deploy a nucleo function. We will call set function, and now, okay, so get artifact URI is how we get our model from the database. So we give the model name. Our model name is MNIST model. We get the artifact URI, which is basically his ID in the database. And we choose the model server class to be what we talked about, the TensorFlow Keras model server. Now let's build our graph. So remember, we have the serving function here, and it has the code of this notebook. So it has post-process and pre-process. So now it's like building Lego. All we need to do is call set topology with an asynchronic engine. And then all I need to do is call graph.to. And what's the first step? The first step is pre-process. What is name? I call it pre-process. From here, I call to, and now I want my model server. So I give a class. The handler is the name of the function. It's, wait a second, it's this thing. See post-process, you see pre-process. This is a handler. but the class name is the model server class. So I give the model server class, I give it a name, I give the model, which we took from the get artifact URI. Then I'm sending it over to the post process, and this step I want it to respond. So respond is closing my DAG, and you can see, okay, let me run it so you'll be able to see. Wait a second. Okay, it's creating the function. Excellent. Now I'm setting the topology and I'm plotting the graph. So I have the pre-process to the MList classifier to the post-process. Now, before I'm deploying the graph, I want to test it locally. So in order to do this, I will create a mock server. I will create a mock server, which is basically a simulator in MLRun. You take the serving function and you call to mock server. Nothing too, too crazy. So we will do that. The mock server will deploy the entire serving graph locally. So the model will now be loaded. Okay, you see a model MList classifier was loaded. Excellent. Now I will read the MList digits and I will call test and I got 5. Now the digit is, wait a second, where it is. Okay, so this is the image. It was 5, and indeed the model returned 5 with a confidence of 99%. Excellent. So we now can deploy our function and pay attention. Everything I need to do to deploy my function as an HTTP endpoint is simply called .deploy. I'm calling deploy. Now it's building the image or pulling the image. The image should be available because I pre-ran it, so it will be available in the cluster, so it won't be needed to be downloaded. Let's check on the Horovod thing. Let's refresh this. Still stuck. Well, sorry guys, a live demo is having live issues. I don't know what broke now. Okay, let's wait for the deploy function. No, it's still on Epoch 1.
The 4.2, is it still local or not?
No, this is, now we are deploying it, a real-time serverless function. You can access it in as an endpoint. You can send it a request and so on. We will do it very shortly once it finished deploying.
Okay, just have a quick question. I guess in this particular talk, you do not include the how to set up feature store and how to monitor, correct?
It's not here, but there is a very good demo in MLRun demos. It's called the fraud prevention. It has a very detailed feature store example and the model monitoring example.
Will you be able to share the link?
Sure. I will do it at the end of the workshop, okay?
Sure, thank you.
Of course.
Sorry, Guy. After
Yes.
deployment, can I share the API link with others so that can they use the application from the
Yes,
side?
of course. Mm-hmm.
Okay,
Yes,
so
it's fully.
Where can I get the link that I can share them with?
So there is a way. I'm not sure about how. Wait a second. I think I can get the path from here, but let's wait for it. Oh, here it is. So that's the link. See, that's my model, and it's live air on the serving graph. So now I can post request to it. Now let's cross our fingers and hope the IPy canvas works. Oh, excellent! It works. It did make me some trouble before. So now we can write whatever number we want. I don't know. I will write 2. And we will get the image from the canvas. They have the get image data. And then we call the serving function invoke, and we will send it over to our model in the air. So now it's invoking. Oh, excellent. What now? Okay. I guess the get image data. Turn it into a list. Wait a second. It's because it's posting it. It must be serializable by JSON because this is how it's being parsed. I guess I need to. Well, this is the risk I took when I used the new demo. Any questions so far? This is the end of the set. Sadly, it's not working as expected, but let's simply do this thing. So this is a NumPy array. Okay.
Maybe it can be related to shape.
Yeah, it's a shape thing. I should check out what I sent there. Wait a second. Array. Okay, and now it is down here. Seems fine to me. Cannot handle this data type. Well, never mind. You know what? I can, instead of using this, I can simply send the image. I hope it will. Wait a second. This is the test image. I will simply send it over. Hopefully, this one. It's the same. Well, I don't know what why it stopped working now, but basically that's the demo, guys. feeling kind of sad that it's ended on this note. But I had good intentions, you know. So any questions?
Yeah, I have a
Now is the time.
question. Yeah,
Yes.
I'm wondering, instead of running on a notebook, is that a link that like end user can click on that link and then it's just drawing there and then provide the predict response instead of going to the notebook? Yeah.
Yeah, the mock server is using the notebook. The mock server is locally. You see now the mock server is using the NumPy array, okay, and it's not going through the JSON serialization or anything. So I'm just sending it here, and it is responding. I'm having some type issues, mismatches, or conversions from.
Yeah,
Yes.
right. So I think we are using different API rather than what I think we should have used MNIST classifier, right? This URL showing at location number 12, right? And at the end where we are predicting, it is showing that it is using some other API, maybe local colon 8000 or something like that. Just up, move up. Yeah, here. SVC cluster local 8080. I guess it is invoking some other function.
Yes, maybe. Wait a second. Maybe it's this one. No, I currently have no idea what's broke it, but if you want, I can show you like another quick demo. Let's do it as a bonus. So I have I have a mask detection demo. It's basically the same demo, but a little bit older. What I'm doing? Okay, so it's using PyImage search code. Okay, you can see here the code. This is the training and evaluation code. Again, it's the same deal. Get model, train, and we have the apply MLRun function. This code is taken from PyImage search, and the dataset is being used. I don't remember, but I must give credit when credit is due. So, sorry. Is by, I'm probably going to read it wrong, but it's by Praina Baadari. She was the one that generated the dataset. So we can simply go and train. We will train it. Okay. We'll create a project. This is, by the way, how you import functions from the marketplace. So in the marketplace, I have a function called Open Archive, and I'm importing the function, as you can see here. So I can download the data from the data source, as you can see here. I already have the data, so I skip this step. This is the TensorFlow Keras. And training and evaluation, okay. Wait a second. So I will simply train. Then you can see I'm building the same as we did before, serving graph, and we will test with both images. This one is with mask, and this one is without mask. And we can deploy a real-time serverless function as well. So let's hope this one will cooperate with us. Okay, training it. You can see it live here. Once the epoch is done, it will be updated. Okay. This is the first epoch summary, and this is the per iteration batches of the epoch. What is important to see is that it's the same code. I didn't waste time on achieving logs or plotting anything, dealing with files, saving something, distribute my training, and so on. All I did was adding this one line of code, and MLRun is taking care of all the rest. So
sorry,
the model should.
yeah. Yes, Guy. All the use cases that we have seen so far are for image processing. Is there any case for NLP, for example?
Yes, of course. We have a lot of customers that are, most of our customers even are using NLP. We have a very cool subject in the Iguazio website. You can go and see someone, don't remember his name, but he's talking about how he implemented the NLP on MLRun. He did very, very cool feature engineering there and serving graph and so on.
Okay, one more question. What about the pricing, the subscription packages available?
Oh, believe me, I have no idea no idea about the prices, money, or what so on. I'm full open source.
Because this is the first question that comes to my mind before moving from one platform to another. So we need to check the subscriptions available before everything else.
Sure, you can reach out to our marketing team for sure, but I'm sorry, I really don't know.
Okay.
Okay, this is our serving graph. This is just some code to print the images, nothing's very serious. Now I'm deploying it to a mock server. Okay, excellent. So this image should be with mask. And so this is locally. This is what you saw already. So now let's deploy. Again, I'm sorry for that it didn't work. If you guys are more interested in feature store and model monitoring, I think we can schedule another like a meetup or workshop or whatever you want to call it, and we can showcase that as well. I'm sure the guys would love to do it. Any more questions while we're waiting?
Do you have NLP use cases that we could reference?
I have a name of a company in mind, but I'm not sure I can say it. So, but I know for a fact that there is a video in the Iguazio YouTube site, or even the Iguazio website itself, which is talking about NLP use cases. Maybe if Bela is here, she may be able to answer you. Wait a second, I will look for her. Bela, are you here? I guess not. I see you guys wrote that you are interested in the feature store demonstration, so I guess I will suggest it. Okay, excellent. Now, okay, now it's working. So again, it's the same prediction because it's basically the same model, but it's live as a serverless function. This is the API, and this is where we post /predict. This is exactly what I wrote. I gave the image, and it processes it. This demo is available again in MLRun demos. Well, that's it. If you have any questions.
Yeah, just a minute. Can you just scroll a little bit up? Slightly. Means I want to see the API path where it was deployed and which we are hitting, right? So there's still showing different locations, both, right? I don't know.
Yeah, I'm not sure about the exact meaning of the URL, but I can assure you it is it is real. Don't worry.
Okay. All right. Yeah.
Thanks. Someone wrote, "Is this the NLP video?" No, it's not. Let's Zio. Let's look it together. Okay, I guess I can tell Bela to send over the example. You guys are more interested in that, and let's see what's more in the slide. Wait a second. So. There are a lot of more blogs, videos, and webinars that you can see and learn from really top and cool guys in the industry on how they use MLRun to accelerate their model development into production. Second, and yeah, thanks a lot. And if you like what you see or saw and everything, you can check us out on GitHub and even give us a star on the repo. And that's it. That's thanks a lot, everyone.
Thank
Thanks.
you.
Bye.
Thank you, Guy. A very
Thank you,
informative
guys.
lesson. Thank you.
Thank you.
Thank you very much. That was superb. And I'm definitely going to be using MLRun in the future. I'll jump on the GitHub and give it a start, definitely.
Thank you. I'm not sure I understand what do you mean from which local host, company server, or if you can explain your question a little bit better. Oh, so the model is stored in the database when we logged it. When it is being deployed on air, you could see that it wrote the model was loaded. So what is being done backstage is that the model files themselves are being downloaded to the pod that we deployed, and then it is loaded from there. Which database? The database that we use in this cluster, I'm using v3.io. It's our own database at Iguazio, but it can be saved in S3 and so on. Sure, no problem. So guys, is there any more questions before I log off? Okay. Continuous trading. Okay, I will write it down.